Hello, and welcome to this video on the quantum model. So we're going to go through what's in the honors workbook, but this information is also really helpful to learn electron configuration at this level, whether you're in AP, reviewing honors, whatever the case may be. Let's just dive in. So first, what is the quantum model? The quantum model is our modern and most precise version for electron arrangement. By the time you're getting here, you've already seen maybe the Bohr model, and you've seen the plum pudding model, all of that. And as we've learned more and more and more, this is our most accurate, precise version of exactly kind of where we can find these electrons based on probability. So with this model, we're representing electrons exactly where they are. There's 4 different levels that we use to write the, quote, address of the electrons. Those 4 levels are called quantum numbers. And then here are my 4 different quantum numbers. So let's kind of go through this different section here to talk about the different parts of the address that we can find our electrons at. So first, energy level is our principal quantum number. And then you can tell I've got little individual ones. We're getting more and more specific as we go this way. So we're starting with our least specific. Our least specific right here is N. So N, it's right here too, but I'm gonna write it bigger because it's quite small. This is our state. We're kind of getting a little bit of an idea of where we can find our electrons. This is all we get with the Bohr model. All we get with Bohr, and it's just an approximate distance from the nucleus. You can tell there's a little Bohr model drawing right there as well. From the nucleus. So that's our n equals 1, n equals 2, n equals 3, n equals 4. And we'll label that on our diagram here on the next page. But that's our generic state, kind of where we can find it, but not very specific. Next up, our second energy level is our orbital quantum number. The symbol for this is L. And this is our city. And this we'll talk more about as we kind of get further down on the page specifically. This is keeping it a little bit generic. These are essentially our orbitals. And they are within an n level. From this. So they're within that kind of Bohr ring is where we find our different orbitals. Our third is our magnetic quantum number. That's m sub L. We're getting more and more specific. These are suborbitals. And just like the name implies, they are orbitals within an orbital. So our suborbitals within an orbital. Getting more and more specific with where we can find our electrons. And finally, our fourth energy level is our spin. And that is our individual unique house number where no 2 electrons can occupy that same space. So for this, we have m sub s, and no 2 electrons occupy the same exact house. And we'll learn how to model spin in a little bit to kind of demonstrate that as well. So let's keep going down. Let's learn a little bit more about N, L, and then our magnetic and spin. So my N, the most specific we get with Bohr, we've got basically it's the energy level or the shell we've already kind of discussed at this point, or you've already learned about. It's represented with a number in front of the orbital. So my N, there's my principal quantum number here, my orbital S, which is my next level, and then my number of electrons that we can find in that. And we'll learn more specifically which numbers in the next section. My orbitals and suborbitals give me more specifically the where in space around the nucleus these electrons are located, and is represented with a letter, S, P, D, or F. And you're going to get real comfortable with S, P, D, and F as we move forward. So my first is an s orbital. My s orbital is every period or shell has an s. It's always where we start when we kind of move down to the next period on the periodic table. These are sphere-shaped. There's only one orientation, which means one suborbital, and it can hold 2 electrons. Every suborbital can hold 2 electrons. So we'll notice, for example, this one, there's only one suborbital. Each holds 2, so we can only hold 2 electrons. These are groups 1 and 2. So we always start when we move down a period with a new s orbital. Next up is the p orbital. And these, you'll see the groups here. We'll have a visual on the next page. You can always pause here and flip the page if you want to. These are dumbbell shaped. There's 3 possible suborbitals, which means, right, if each suborbital holds 2, then we can hold, therefore, 6 total electrons in each p orbital. And this is a note here on why we have only these 3 pictures of those suborbitals. So there's 3 versions of p with different orientations, but the same energy level, they degenerate. All right, good. Next up is the d orbital. That's our transition metal block. You can see now we have our visual. So here's S, we talked about S, then P, and now we're talking about D here. They're four-leaf clover shaped. There are 5 suborbitals in these d orbitals. There's 5 subs, which means total of 10 electrons can be held here, 2 for each of the 5 suborbitals. And then finally my f orbital. Those are my rare earth metals here at the bottom. I'm going to teach you about them, but we tend to not use them too terribly much. They have 7 suborbitals. You can see they're kind of crazy, clovery, extensive shape here. 7 suborbitals, each holding 2 electrons, means it can hold a total of 14 electrons for each f orbital. Last up is spin. And my spin, we represent the exact house number of those electron pairs. So it's a property of electrons that relates to their magnetic field. That's why it's called spin, spin up or spin down. We represent spin up with an arrow up, spin down with an arrow down. And then we fill these kind of as pairs. You'll see when we get to our orbital diagrams what these kind of look like. But we represent that in each particular suborbital, the 2 electrons that it holds have opposite spins to demonstrate that they are not occupying the exact same space. So here's my diagram. So we've got my S, D, P, and my F block down here. So first let's label our N, right? Our principal quantum number. So we've got N equals 1, N equals 2, and these are just the period numbers that you are familiar with from previously. N equals 5, N equals 6, and N equals 7. And then we'll make a few notes on how we list the other ones, because this is probably going to be the most useful part of this, is this little diagram here. So for my d orbital here, my d orbitals as we're going down, we consider these what's called n minus 1, which means our numbers are minus 1 of the level. And that'll make more sense when we get to the next part. But basically, even though this here is in the 4th period, it's 3D. So it's n level 4 minus 1 because of how the electrons fill the shells. That's why that's listed. It's a number earlier because we're going to fill this 3D level before we fill the 4th level. Down here, you'll notice 4 and 5, even though these fit right here, right? So technically it should be 6 and 7, right? But my F orbital, we have n minus 2. So we've got 2 levels down for both of those. So that's where the 4 comes in, right? 6 minus the 2, that's where that 4th comes in here. Okay, so let's start using this to actually write some electron configurations. So it's how we represent all the electrons of an atom using that quantum model. We start from our lowest energy level, so at the top of the periodic table, we can add that, top of the periodic table. We're gonna start up here, our lowest principal quantum number, and then we're moving down, across and down, according to whatever the electron configuration is. So use the periodic table to guide you, particularly use this periodic table to guide you, very helpful. What does an electron configuration communicate? So here's our little example, let's go ahead and label it. That number 2 is our energy level, or N. My letter here is my orbital. That's my L, right, from our house address. And then the number up here at the top, that's my number of electrons in that orbital. Okay, so now let's actually practice. I'm going to make a couple of notes first, and then we're going to use this, keep this visual, and move to the next page. If you don't have this page and you're following along with us, then pause here and take a quick screenshot of this, and then save that so that you can use it for the next time. Got it? All right, moving on. So I have some notes up here to go over first. We're going to talk about those after we do carbon and titanium for the purposes of it'll make a little bit more sense. So let's start with our expanded electron configuration. We're just going to start like our instructions told us, right? Our instructions told us we're starting from the lowest energy level, so we're starting at the top, and we're just listing as we're going down. So I'm going to keep this handy. We'll probably go through this and use it at the same time. So first thing I want to do is find carbon. So on my regular periodic table, I can locate that carbon is right here. I might just fill in a little C to keep us on track there. And then I need to list everything up until carbon, and that's going to be a unique electron configuration just to carbon. So the first thing I see is 1s, and the 1s is full with its 2 electrons. So I'm going to start by writing 1s2. That tells me my 1s orbital is full with its 2 electrons. 2s is also full. Remember, my s only holds 2 electrons, so 2s2 1, 2 is also full by the time we get to carbon. Next up, if we're just reading our periodic table, is the 2p orbital. So 2p, and then 1 and 2. There's only 2 electrons in carbon in the 2p orbital. 1s1, 2s2, 2p2. So our note here, last orbital you fill is the highest energy orbital, right? So we get to our highest energy 2p. That's the last one we fill. We go down in order. The orbital with the largest principal quantum number, or orbitals, are the valence electrons. So for carbon, we probably already know how many valence electrons carbon has. It has 4. We could use this electron configuration to figure it out. My largest principal quantum number here is 2, and represented in my 2 level, I've got a total of 4 electrons, right? 2 plus these 2. So that tells me that carbon has 4 valence electrons. Pause the video here, try out titanium. All right, hopefully you paused and you did titanium. Let's do it together. First thing I want to do is find it on my periodic table. Titanium is right here, and I'm going to do that same process. So 1s1, 2s2, it's going to start the same. 1s2, 2s2, because those are both full. Now my 2p in this case is also full. So 2p, and my p orbitals are full with 6 electrons, but you could also count 1, 2, 3, 4, 5, 6. But we got to keep going because titanium's down here. So we're done with p. I'm going to keep going. 3s2. I'm going to keep going here. 3p, 1, 2, 3, 4, 5, 6. Then we keep going. 4s filled with 2. And then last up is 3d, 1, 2. 3d, 2. Perfect. Hope you did it right. Now, the next part is our shortcut way, the noble gas configuration. You can even add that. This is the shortcut way. You can imagine as we're getting to giant, even titanium is pretty long, but as we're getting to these bigger and bigger elements, we're going to get really, really long electron configurations. So my noble gas configuration is where we use a shortcut and we list the most recent noble gas and then just list what's after that. So for example, we can practice with titanium real quick. So titanium is here. If we go backwards, my noble gas next to where titanium is, this is argon right here. So instead of writing all of this, I could just write argon and then list the part after it, 4s2, 3t2. So that would be my noble gas configuration for titanium. Let's do magnesium, or you can pause here and try magnesium and chloride on your own. So for magnesium, we find it on our regular periodic table. Magnesium is right here. My noble gas before magnesium is neon. And then all I have to do is list what's after neon, which in this case for magnesium is just 3s12. That's it. So if you haven't already, pause for chloride. Now the trick to chloride is we have another negative here. So we're going to write the electron configuration out and then account for that extra electron, right, as we're going through. So chlorine is right here next to argon. So it's also neon as its previous noble gas. And we're going to start with neon and then list what's after neon all the way to chlorine. So we've got 3s2 and then 3p, but my 3p here would be 5, but that's for non-ionic chlorine. That's for chlorine. Chloride, my extra electron, wouldn't be 3p5. It has an extra electron, 3p6. And let's probably want to add a note for that, right? Extra electron for ion. For ion. Now, this is also a really good notice, right? We know my noble gases are most stable because they've met the octet rule. So this is also a good illustration of why chlorine likes to gain an electron, right? It goes from being very unstable to being just like argon in its electron configuration. All right, so the next part here is I've added some practice problems, and that for some of you may be the last part that you see. If you're watching this video for AP or I've requested it, whatever the case may be, then we'll do orbital diagrams after that. But first, just practice with 4 additional problems for your electron configuration. So we've got oxygen, nickel, arsenic, and neodymium. So go ahead and pause here and do that. All right, So I've gone ahead and filled in the answers here so you can check your answers. Again, pause, check your answers. I've done both the standard configuration and the noble gas configuration, so you can check both. It is really good to make sure you can do the entire thing before you start using noble gas, so hopefully you went through and did both. Or you can pause and go back and do both, I suppose. So now let's get into orbital diagrams. Orbital diagrams is kind of our last component here. So for orbital diagrams, we're going to start with our kind of definition. What is an orbital diagram? An orbital diagram is a visual representation of your electron configuration. So this is kind of messy and hard to read. Basically, it's this same thing, my electron configuration, but mapped out in a little bit more of an appealing, organized fashion. So the key rules for creating an orbital diagram are listed below. We have the Aufbau principle, Hund's rule, and the Pauli exclusion principle. So let's list what we're kind of getting, what information we need from both of those, or from all three of those, excuse me. So Aufbau principle, my electrons fill from lowest energy level to the higher energy levels. Hund's rule, electrons fill individually. Each suborbital before they begin to pair up. They much prefer their own space. Remember, electrons are negative, they repel each other. And finally, the Pauli exclusion principle means that no electron can have the exact same address. Which means that paired electrons in a suborbital must have opposite spins. So that's that last component, that M sub s, that we haven't talked about yet, is spins. And that's what we'll show with our orbital diagrams. We don't need to worry, right? As we're doing our electron configuration, we have groups of 2, 4, 8, 10 different electrons. But my orbital diagram is going to really map out the individual pairs of electrons according to their spin. So let's practice that on the next page. So first, some rules for how we're going to create this orbital diagram. First up, I've done for you, is your electron configuration. We're doing carbon and titanium from the previous page. Starting with the lowest energy orbital, you're creating a dashed line to represent each suborbital within that orbital. For example, for 1p, draw 3 spots to represent the 3 orbitals in p. For example, you would draw 1p, 1, 2, 3. This tells me I have space in my 1p orbital for 6 total electrons because each of these dashes can hold a pair of opposite spinning electrons. Represent all of the electrons in your orbital. Check the exponent to know how many arrows to add. Add 1 electron with an upspin to each orbital. Only if all suborbitals are filled are we adding our downspin, right? You saw how I filled that in. All the upspins, and then if we have more, then we start to pair them up only. So let's do carbon as an example. We start with our lowest energy level, which we write on the bottom. So we're starting with my 1s2. How we list that out? Just like we did here. 1s. And 1s, remember, has only 1 suborbital. In this case, there's 2 electrons in it. 1, 2. Now we move up to higher energy levels. 2s, I'm going to do the same thing because there is a pair, 1, 2 electrons. Lastly, 2p, I'm going to write to the side after those electrons. My 2p has 3 suborbitals. 1, 2, 3. This 2p orbital only has 2 electrons. 1, 2. And we're done. That's carbon. Pause the video, try titanium. Welcome back. So we're going to list titanium the same way. I'm starting at the bottom. I'm leaving myself a little more space because we've got some extra orbitals here. 1s, 1, 2, 2s, 1, 2. We're just continuing down the line. 2p, 1, 2, 3. There's 6 here. 1, 2, 3, 4, 5, and 6. Back to s, 3s. 1, 2, back to p, 3p, 1, 2, 3, 1, 2, 3, 4, 5, 6. Where am I at? 3p, 4s, 4s, 1, 2, and finally 3d. I should have left a little more space because this should be above, just so you know. So we're going to the very end, right past p. My d orbital, right, there's 5 suborbitals. 2, 3, 4, 5. But I only have 2 electrons. 1, 2. There's your titanium orbital diagram. All right, that's it for this set of note. Feel free to rewatch as needed.